Hello again from the posh lavish digs of Mill City Roasters, or more precisely, the Mill City Roasters booth at the 2018 SCA Expo in Seattle, Washington, just for grins. I'm Steve Green. I'm responsible for everything, and mine are the views of Mill City Roasters. A recent post on one of the forums sparked a discussion about the use and relative value of variable fan and drum speed. Do you need this type of control for better coffee or not? Well, like everything else in coffee, it really depends on what kind of roasting you're doing. Old school manual roasters had rudimentary controls. Now, fixed airflow forced the operator to stand next to a howling exhaust fan all day with the volume of air controlled by diverting it somewhere other than the drum, usually through a cooling tray. Drum speed was similarly fixed at a rotational speed that someone thought was most likely to succeed with a full batch size relative to the range of airflow adjustment and the thickness or conductivity of the drum. Now let's take a rabbit trail for just a moment and talk about the actual heating mechanisms of commercial coffee roasters. Heat is said to be kinetic. That means that heat is actually motion. In this case, it helps to think of it as vibration. Conduction occurs at a point-to-point contact when the faster vibrating molecules of a solid heated object physically contact the slower vibrating molecules of a solid cooler object. In this case, the point-to-point contact conducts some of that vibrational energy to the cooler object, and voila, heat's transferred. In your roaster, conduction is bean to drum and bean to bean. Now, successful, highly conductive roasts tend to be slightly less complex with a tendency to manifest darker chocolate and caramel flavors. Conductive heating is similar, but in this case, the molecules of heated air, aka the fluid media, surround the cooler solid object and pass energy via the entirety of the exposed surface area. Because coffee absorbs the heat more uniformly, convection is a more efficient transfer of heat and drives the roast faster. This can preserve more complexity and differentiation in the cup, but sometimes moves a little too fast at the cost of body and pleasant, lingering, darker flavors brought out by more conductive roasts. Hey, this isn't science, it's cooking. I'm looking for descriptors that work for all of us here. The most mysterious form of heating is infrared radiation. The sun is an excellent example. Although 93 million miles from Earth across the vacuum of space, it emits enough infrared radiation to reliably defrost my home state of Minnesota nearly every spring. Infrared radiation is emitted when materials are heated beyond the state that they can absorb that energy, with some portion of that energy released as infrared. Now, you physics guys probably have a better explanation for all of that, but honestly, nobody roasting coffee for money cares. One thing that is interesting and somewhat relevant to roasting coffee is the fact that as your roaster gets hotter, it radiates heat off at an increasing rate. So Scott Rao's ideas about a decreasing rate of rise profile were very likely sparked by the coffee quality of those ancient and clunky old probats, where the on-off control burners, cast iron front and rear plates, fixed airflow, double-walled drums allowed an operator to peg the heat to first crack, shut the burner off, and coast to a solid development, and when everything lines up just right, actually get a pretty good cup. If you install a bean temperature thermocouple in that old machine, you'll sometimes see a naturally declining rate of rise to that roast. It's pretty neat, and an idea that we actually try to emulate with the construction of our roasters. The commercial drum roaster is said to be about 70% convective and 30% conductive, so where's the infrared? Well, good question. The answer is, we don't really know. Infrared requires line of sight. So a solid-walled drum roaster, there's only a very low amounts of infrared transmission as the heated metal of the drum radiates IR into the bean mass, so low that we do not have any easy way to measure that effect. However, if you are roasting on an electric roaster with a perforated drum, IR can pass through the perforations and penetrate a maximum of about 1.5 millimeters of the surface of the coffee bean. So one thing to bear in mind with perforated drum electric roasters is that bean color is always darker at any given roast level due to surface absorption of infrared heat. This often leads to darker than expected but still underdeveloped coffee. But I digress. Back to the roaster. Here's a handful of variables that someone probably should have thought about when they built your roaster. Drum diameter, drum depth, mixing vane geometry, heat source, airflow, conductive heat transfer characteristics, convective heat transfer efficiency, and the big one, batch size, because batch size changes the way that all of this stuff works together. With fixed settings, problems with any of these often manifest as scorching, tipping, facing problems with ROR, problems with chaff removal, or burned coffee flavors related to heat defect, with the result that all is sadness. So what's a guy to do? A modern and well-equipped roaster should probably provide you with the option to tune the drum speed or change the airflow relative to batch size to optimize conductive, convective heating ratio to the desired flavor profile. That means that for any given coffee, because each coffee can be weirdly unique, you'll be able to roast at maximum capacity with the best possible roast quality and keep your production at maximum efficiency. So do you need variable drum speed or airflow control for better coffee? If you're roasting the same coffee at the same batch size to the same roast level, maybe not. If you're roasting different coffees to different roast levels and different flavor profiles, you probably do. I'm Steve Green from the cavernous halls of SCA 2018 in Seattle. Thank you and good night.